Hello, welcome back everyone. We can start the new session. Please welcome the next speaker, Virgile Robles. And Virgile holds a computer science PhD in Paris-Saclay University. He specializes in security for critical system and formal methods. When working on SpaceOS, he is leveraging his experience obtained at CYSAT and Twig, and his passion for designing robust and efficient systems. When not developing space software, he enjoys training other engineers about software verification and high-performance algorithms. Well, thank you. And
thank you for being here. So I'll try to talk to you about SpaceOS, which is an operating system and not really an operating system, as I will. Sorry, thank you for the mic. I'll try to talk to you about SpaceOS, which is both an operating system and not an operating system that we are developing at Parsimoni. This will be a fairly high-level talk about what we do, why we do it, and an announcement at the end about an event that we are organizing in the next month. So I'm first going to make a point that I think the room is already convinced about, mostly, that onboard computing in satellites is useful. So I'll be quick over that part. But in a lot of Earth observation cases, when we have a lot of data to analyze, but a few insights we want to report back to the Earth, it's very useful to eliminate a lot of useless data, as you know. So by sending all of the data, we have a lot of data to send, and obviously a big bottleneck and costly bottleneck of sending data back to ground. And even a few pre-processing steps on board are very useful to reduce that bottleneck. So it can be as simple as filtering useless tiles that are probably full of water in this case, if you want to detect boats in this image. But the more processing power we have on board, as you know, the more precise the insights that can be computed on board. So we can go deeper and have image inference on board and detect actually where the boats are and just send the coordinates instead of heavy images to compute. I believe I'm just talking to a convinced audience about some of this. But this raises a few questions about the hardware, how to use it. Onboard computing is very expensive, both in terms of hardware to send, power in particular. So it must be used very, very efficiently. Like every part of it must be exploited to the maximum. And so both in terms of capacity and in time. Meaning that in a lot of missions today and probably in the future, when we have one mission per satellite, a big part of the orbit is spent idle by the satellite because the zone of interest is over and we don't have anything left to compute, potentially. So having any way to make value out of that idle periods when talking to various partners seems to be very useful. So any way to share that period of idle time, both for sensors or compute with potentially other partners, is very interesting to us. But this raises a few other questions. One of them is, of course, security. If we have more stuff on board, more computing hardware, more complex operating systems to handle all of this hardware, and no potentially other clients, other software payloads next to our ones, that's a lot of attack surface that is exposed both for the satellite operator, which don't want the life of the mission to be affected by the just processing software payloads, but also between each other, between the payloads. Like if there is proprietary information in one software, it mustn't leak to the other ones on board, either through the use of CPU, memory, or acceleration hardware like FPGAs or GPUs. And lastly, and this is still a bit about interoperability, embedded software development is complex, as you know. It's very specific to a given stack, a given vendor, like Xilinx, NVIDIA, a lot of time is spent adapting to that stack, both software and hardware. So we believe that when possible, it's not always the case, applications should be as portable as possible. Of course, there are a lot of obstacles to that, both the hardware, not everything is compatible between each other. Sensors can vary a lot between satellites. So there's only so much we can do, but where we can, at least basic functionalities of a satellite should be accessible in a, if possible, standard way, at least in a common way, that can then be adapted further to the specific hardware, sorry. But the basis should be easy. So this brings me to some of the survey we've done of the operating systems in satellites. And we call that kind of the middleware gap. There is a lot of effort spent on either very optimized operating systems that are not that flexible. They can be very extremely secure, like using PikeOS, for example, as an hypervisor with rigid partitions that isolate different payloads. But then when we want to change the mission post-launch, it's very hard. And on the other end of the spectrum, you have like ground frameworks adapted for space, like Linux, plus huge orchestrators like Kubernetes or variants. Like, don't mind too much the placements of these various products. It's very arbitrary, but it's just a tendency that there is a spectrum from very optimized in terms of resource usage, but not so flexible, but most of the time very secure. And at the other end of the spectrum, heavy in terms of resource usage, but very flexible and easy to develop for. Of course, Kubernetes and Linux on satellites can work in some cases, and to each their own. And I'm not arguing that defense missions should run Linux instead of heavily secured hypervisors. But we believe there is room for solutions that make some trade-offs between heavy solutions like Linux-based solutions with plus big orchestrators and heavily constrained solutions, especially if these solutions can be in some way interoperable. One of the technologies we are very interested in and try to leverage for that is something called unikernels. Unikernels is some technology that comes from research in the University of Cambridge from about 10 years ago, and we've been very involved in its development. And basically, it's just the application of the concept that everybody knows, that specialization in any domain is performance, but applied to operating systems. The basic idea of unikernels, of which there are many different implementations, but the concept is the same, is that instead of starting with a general purpose operating system, which has a lot of available components for like the user space, the libraries, all of the dependencies that you can use, and the kernel components, so the base functionalities of the OS, we start from a given application. So when we know exactly what we are going to run on some piece of hardware, we can select in each layer, both in user space, in dependencies, and even within dependencies, and the kernel, what is needed for that specific application. This is very high level, but you'll find more details in the links I will provide later if you want. Selecting these components in each layer and assembling all of these components in one shared memory binary is what we call a unikernel. So we start from a given application, and from a library of small bricks of pre-existing components, we assemble a special purpose operating system that, combined with the application, is a full-fledged VM, virtual machine, that can be executed on common hypervisors like KVM and many others. This is the base concept, and the reason to do this is twofold. On one hand, it allows to have actual virtual machines for like less of the usual overhead associated to virtual machines. Like one legacy, maybe I'm exaggerating a bit, but a way to do VMs is to virtualize a full operating system for my applications. Of course, the solution to that is usually done is containers, which are really great and work for a lot of applications. They allow to share some resources between different applications, share the Linux kernel in most of the case. Give away some security. We don't rely on hardware hypervisors. We still have some nice isolation though, but we give some of that away. And when we are talking about potentially embedding software from completely different entities in the same space, handling different resources, we believe at least that if we can, it's not always the case, but leverage hardware isolation without a lot of the overhead, then it's worth doing it. So that's the basis of what we use within SpaceOS. Basically, it's a runtime that can use various hypervisors to run unikernels. And most of the interest is providing an interoperable SDK to develop these unikernels, but I'll come back to that a bit later. Just to give a few metrics, in one use case, we've worked with Thales Alenia Space in the past on one example, an image inference software that just takes images taken from the sky and detects where is the satellite in the picture. We probably cannot see it very well in the top, but there is a satellite. Basic neural network. When packaged in their way, it was an adapted ground framework, so full Kubernetes, Linux distribution, a heavy stack to run it. Of course, you can always try to optimize that, but it's not always so easy. But in this case, we were kind of lucky, and we first managed to replicate completely the functionalities of the applications while packaging that in a unikernel. But we reduced the size by 20 times. So we went from, like, if I remember correctly, 200 megabytes to the order of a few megabytes. Of course, it's not always that magical. If the application is already very well optimized, then we cannot have that much gain. Like if your application embeds 1 gigabyte of data, we cannot take that away. But it showed that with some automated mechanisms, you can achieve a lot of trimming out of the unneeded dependencies of one given application and gain security in doing so. You can sometimes notice some runtime performance improvements too, because there is, for example, less switching between kernel space and user space, because everything is the same kernel, but whatever. This is not that much the point. Speaking about interoperability, like unikernels are one thing. They provide security for not that much overhead, but it can be a bit harder to develop for unikernels than for containers. So it's all about trade-offs. One thing that we are pretty adamant about is trying to, again, make development as easy as possible. So the idea is that not only SpaceOS is a runtime for unikernels, it's an API that can, or should, it's a work in progress, provide access to some basic functionalities of any satellite when possible. So this is things like clocks, orbital data, intra-sat communication, so in internal network, up and down link, and so on and so on. With security built in and not as an afterthought, meaning that as soon as we are talking about sharing different resources on board, like sensors, potential hardware, we have built in the notion of rate limiting, access sharing, and generally the arbitration of how shared access to different resources is managed. So this is mostly the functionality that we offer, plus a few tools to easily manage payloads as unikernels. And this is even more work in progress because there are a lot of obstacles and questions to solve, but something that is very interesting to us is to, when possible, have that interoperability even for hardware accelerated stacks. We are working in particular in some European projects with partners to provide an abstraction for applications to make generic calls for accelerated computation, like image segmentation, compression, general purpose operations that then, depending on the mission and deployment, can be matched to actual implementation of Xilinx, of TensorFlow, of the actual stack that is present on board. But the application itself uses these abstract calls and does not need to be rewritten from one mission to another, at least not on these parts. Of course, there's a lot of complexity hidden there. Like models have to be trained for different sensors in particular. Vendors can be extremely different. So it's not that easy, but we think that it's a goal that is worth working towards too. But again, we don't want to develop in the void just a new standard. We know how that goes. So really the goal for us is to collaborate with as much people as possible to understand the needs of various missions and not necessarily try to define our own standards and impose it to everybody. That will not work, but rather to form some consensus for some functionalities of the satellites that can be shared amongst different software stacks. So we are very interested about any discussions or ideas you might have about that. So all in all, what the hell is SpaceOS? It's not really an operating system in itself. It's a suite of tools that can be assembled potentially as a full distribution. So it's first a sandboxing model. You choose an hypervisor if you want to use unikernels. That's what we do. So just Linux as a base and KVM. That's one easy possibility. But it can also be something more niche like Muen or Xen or SCL4, but any hypervisor that we are compatible with. We are not compatible with everything, of course. And then you choose what you want from SpaceOS, basically. If you want just the runtime, the ability to be compatible with existing unikernels, you can have that. We are working with partners to do that. If you want the full distribution that we provide, Linux-based or with another hypervisor, we can do that as well. Everything is not completely production ready. We are working with different partners to try what is the best form to propose these ideas. But that's the concept. Virtual machines as a basis, but even that is not always the best solution for a mission. So we are very interested in WebAssembly, as many of you are also, or even containers. But mostly having security built in the solution and in the rope. These are the ideas that we really are attached to. And now I'm going to a little announcement that I wanted to make. Today we are launching a hackathon for a duration of 1 month. We want to test some of these ideas of security on board. So what we are doing is that there is a web portal that you can go to right now if you want to, called hacksat.dev. It's a little rough around the edges, but be gentle with us. The idea is that you are able to upload arbitrary unikernels. So there are a lot of documentation and instructions of how to build applications into unikernels. There are 2 different implementations of unikernels. One is called Mirage. It's based on the OCaml programming language, which is pretty niche, but we like it very much. But the other one is more standard. It's called Unicraft. Both are open source, and you will find a lot of instructions about them. And with that, you can just program application in C, C++ in a standard POSIX way, and hopefully it will work as a unikernel. And so through the web portal, you will be able to upload these pre-built unikernels on your machine, and these will be distributed to several actual onboard computers that were generously lent by some of our partners. So we have the DeFi Space OBC. So we have partnered with DeFi Space because they share a lot of our vision. They want to build, design and build a shared platform for software on board of satellites. And they try to make streamlined solution that embeds high efficiency CPUs, GPUs, and NVIDIA cards, and a streamlined interface. So we try to collaborate towards that. We also have a board from Thales, the LX2160, that is a standard ARM board, and a board from Colossus Crystal. And we have Jason from Colossus right there, if you want to say a few words about his company.
Hi there. I'm Jason. I'm the CEO and co-founder of Colossus. And our focus is on the hardware layer of the tech stack. So our focus specifically is on data processing systems, so high performance CPU, GPU, FPGA, and more coming down the pike. We're proud to partner with Parsimoni to provide that kind of middleware layer, the software infrastructure that makes everything work, and provide easy to use and, more importantly, secure platform for the application software, which is the whole reason that we're doing what we're doing. So if you want to learn more, I'll be over at the Parsimoni booth, and we might have a demo to show you. Thank you.
Thank you, Jason. So coming back to the hackathon, the goal is, if you want to, try to upload arbitrary programs and to hack these onboard computers from the inside. So we will not check what you upload, not audit them. They will be deployed as unique kernels virtualized on these computers with some access to API to access some of the onboard capabilities. And your goal, if you accept it, is to try to exploit it or just build something interesting with it. And we have so this web portal that you can access to manage, upload things, and monitor applications. I will put the URL at the end again. On board of the computer, you will have different applications by different people, access to some kind of bus manager, which arbitrates the shared use of resources that, like I mentioned earlier, and access to some capabilities on board. So today, the features are bare bones. You can just check that you can interact with the system, but as the month progresses, we'll add more and more features that you can access from the satellite. And so yeah, you can try to both attack from the inside the host, you can try to attack each other if you manage to, or the general infrastructure that is used to deploy unique kernels. We have two kind of tracks, some kind of exploit challenge. So we have different goals that you can work towards to if you manage to. And if you manage to hack something and can prove it to us, we can reward you money for that. We have some pool of money locked for that. But if you prefer to just play around with the sandbox, we're also, thanks to DeFi Space, proposing like a use case challenge. So you can try to build an interesting program that makes use of the few functionalities that we expose. It's relatively limited, but it's a first. And judging your submissions, if you want, with DeFi Space, will award the one we find most interesting or that uses the most of these functionalities to go to space, actually, and to be embedded in the next mission of DeFi Space on their satellite. So if that's something that interests you, that go ahead and try it out. That's it. These were a lot of ideas, so I'm welcoming any feedback. If you want to, head to the web portal. Hopefully, nothing explodes in the next hour. Thank you.
Thank you, Virgile, for the talk. Well, now it's the time for the questions and hopefully answers. Do we have any question in the room? No, we don't have online, but I have a question.
Sure.
In the example that you made from Thales, I think it was, that you work on, you mentioned that it's easy to update and maintain. A question arises a little bit. Is it actually easier to maintain a unique kernel when you have a lot of dependencies mixing like different layers and stack?
It's not that much easier than containers, for example, but it is a lot of work to provide the tools to do so. Like, one of the value from any platform, be it ours or DeFi-Space, only one, is to have a streamlined suite of tools to do all of these operations. It's like taken as a natural thing today, but just to mention that all of this is thought about and part of the product, not just it's not just a low-level OS managing unicals. It's supposed to be an actual easy-to-use product. So nothing about it is necessarily easier to manage than containers. That's not the case, but it should be as easy.
Okay, thank you. Any question in the room? Maybe a question? Okay, no? Then thank you again for the talk. And